Chapter 3, Derivatives. 3.1, Derivative of a Function, Part 1. Your objective for this lesson is to find the derivative of a function. Okay, so first let's see what we're talking about when we say derivative. We have the definition of a derivative here, and you can see the derivative of a function f with respect to the variable x is the function f prime, so this is f prime, whose value at x is as follows. You see f prime of x equals the limit as h tends to 0 of f of x plus h minus f of x over h. So this should look familiar. This is your instantaneous rate of change. So this is coming back again, very important. And this is provided that the limit exists. So if the limit does not exist, then you don't have a derivative at that point. Or of the function, I should say. The domain of f prime of your derivative is the set of points in the domain of f, your original function, for which the limits exist. And this may be smaller than your original domain. So if there are some points for which the limit does not exist, then those get left out. Your domain is smaller. Okay, and if f prime of x exists, then the function f has a derivative at x, which is the same thing as saying it is differentiable. So has a derivative means that it is differentiable at x. A differentiable function is differentiable at every point in its domain. So that's pretty straightforward. Example 1, we want to differentiate or find the derivative of f of x equals x cubed. So I'm going to go ahead and write down the definition that we just got. F prime of x equals the limit as x, not x, as h tends to 0 of f of x plus h minus f of x all over h. And from here we can just go ahead and plug in. We know f of x is x cubed, so we'll say the limit as h tends to 0 of x plus h cubed minus x cubed over h. Okay, and now we need to expand this. So let's do that. So x plus h times, well, I'm going to have this 3 times. I know that x plus h squared is x squared plus 2xh plus h squared. So I'm going to write that out here to save myself a little bit of work. And now we just have to multiply this in. So my x's, so x times x squared is x cubed plus 2x squared h plus x h squared. Okay, now we have to multiply h in. So let me get rid of these. So h, h, h for all of them. We have, I'm going to put my x's first because I have x's first here. So x squared h plus 2xh squared plus h cubed. Okay, so this is that. And I'm going to add back on or subtract my x cubed again. And this is a big line. Okay. So let's combine like terms because that is definitely unruly. x cubed and x cubed I have, these are going to cancel because they have different signs. So those are gone. Thank goodness. I have x squared h here and here. So we have the limit h tends to 0 of 3x squared h, okay? And then we have xh squared twice. So plus 3xh squared plus h cubed over h. And you know from here, I have an h in each term, so I'm going to cancel out one h from each of these. That goes away, gone, that's gone, this becomes a 2. So we have the limit of 3x squared plus 3xh plus h squared. Okay. And now you know that what you're going to do to evaluate the limit as h goes to 0 is plug in a 0 for each h. So we get 3x squared plus 3 times x times 0 plus 0 squared. These cancel, and we are left with 3x squared. So this is our limit as h goes to 0, which also makes it the derivative of the function x cubed. So this is the derivative of y equals x cubed. Not too bad. It's something that you've already done before. It's just a lot of simplifying. That's what it is. Okay, so now we have a second definition, your alternate definition of a derivative. This is a derivative at a point. So before we were just looking at the derivative of the entire function. Now we're looking at a specific point. So the derivative of the function f at the point x equals a is the limit f prime of a equals the limit as x tends to a of f of x minus f of a divided by x minus a. Again, this is provided that the limit exists. And you can see it's a pretty similar function here. Okay, so example 2. Differentiate f of x equals the square root of x using the alternate definition. So I know I'm going to use the alternate definition. I'm going to go ahead and write that down here then. So f prime of a equals f of x, oh, not f of x, sorry, the limit as x tends to a of f of x minus f of a over x minus a. Okay, there we go. And we're just going to plug in what we have. So this is the limit x tends to a. We know f of x is square root of x minus, if you plug in an a, you'll have a square root of a if you plug an a into that function, over x minus a. But what I want to do here now is rationalize the numerator. I know I'm trying to simplify. I don't want to have both an x and an a in here. So I'm going to rationalize the numerator. Okay. And let me move this over just a little bit so I can do that. So I want to multiply by the conjugate here. That is square root of x plus square root of a. That will get rid of the square roots up top. Do top and bottom. It's just like multiplying by 1 when you multiply the same thing top and bottom. Okay, and when I multiply out the tops here, this is the same factorization as for a difference of squares. You see the same terms first and second and plus minus. That means we have a difference of squares. So I'm just going to write that out. This squared is x, this squared is a. So x minus a is what I'm left with on top. On the bottom, I have an x minus a also times what we just multiplied in, that conjugate from the top. And you can see these two factors just cancel. So it helps to sometimes not multiply in right away so you can see this canceling. Okay, so we're left with the limit x tends to a of 1 over square root x plus square root a. And let's go ahead and take this limit. So I'm going to plug in a everywhere that I have an x. So this is 1 over square root a plus square root a, which is 1 over 2 square root a. So this would be the derivative at the point a. So this is derivative of, of f of x equals square root x at x equals a at that point. If you wanted this to be for any point in the function, then your derivative f prime of x would just be 1 over 2 root x. So this is for any point in f of x. Okay, so that's the only difference between these two. This is general, this is specific. Okay, last part for this video, we're going to talk about notation. So there are a few different ways that you're going to see derivatives written. This is on page 97 in your textbook. The first way is the shortest way to write. You can just write y with a little apostrophe up here. This is y prime. You've heard me say f prime a few times now. And this is nice because it is so brief, so short. But the issue with this sometimes is that it does not name the independent variable, and sometimes that's very important. So you can't really always use this. Okay, dy over dx, dy dx is the derivative of y with respect to x. Most of the time you're not going to say this whole thing out, you'll just say dy dx. And this is nice because it does name both of the variables. D stands for derivative. df dx is the derivative of f, that's your function, with respect to x. This really emphasizes the function's name, which you may need to want to do. And last but not least, we have d dx of f of x, which is the derivative of f at x. This emphasizes the idea that differentiation is an operation performed at x. So it's an operation, not like a multiplication problem. So these are 4 different ways that you may see derivatives written. You do need to be familiar with all of them, be able to work with all of them. You're not always going to get to choose what you get to work with. So that is part 1.